This video aims to explain what's going on in the equilibrium system involving the copper-ammonia complex. We begin this experiment by adding a clear, light blue aqueous solution of copper 2 chloride into the beaker. In this solution, the copper chloride has dissolved in the water into its ions, copper 2 plus and chloride negative. Because of the copper and its metal bonding structure, when it is dissolved, so in solution form, it reacts with the water, forming a complex ion called hexaaqua copper. A complex ion is when a metal ion, in our case the copper, is at the center with a number of other molecules or ions surrounding it, which in this case is the 6 water molecules. These are known as ligands and act as a Lewis base, electron donors, and the central atom acts as a Lewis acid, the electron acceptors. These are attached to the copper ion by coordinate bonds, which is when the oxygens share their lone pairs of electrons in their outer energy level to the copper ion. The overall effect of this bonding is that each of the hydrogen atoms is more positive than it is in an ordinary water molecule. The 2 plus charge is no longer located entirely on the copper ion, but spread out over the whole complex ion, much of it in the hydrogen atoms. This complex ion has a 2 plus charge and is highly soluble in water, thus giving rise to the characteristic pale blue color observed in the solution. This system is at equilibrium. Both the rates and concentrations remain constant. It also means that both species are present, both the copper ions and the hexaaqua copper ions. We then add an ammonia solution to the system. Ammonia is a weak base, and so in solution with water, it forms an equilibrium, dissociating into hydroxide and ammonium ions. As we said before, the hydrogen atoms attached to the water ligands are sufficiently positive. Initially, with a small amount of ammonium hydroxide, 2 of the water ligand molecules are deprotonated by the hydroxide ions to form 2 hydroxide OH ions. What happens is that the highly charged hydrogen ions from the hexaaqua copper ions are pulled off by the hydroxide ions in an acid-base reaction. The complex ion is acting as an acid by donating a hydrogen ion to the hydroxide ions in the solution. The hydroxide ions from the ammonia, of course, acting as a base by accepting the hydrogen ion. This occurs in a stepwise process, so one hydrogen is removed at a time. Once the hydrogen ions have been removed from 2 of the water molecules, you are left with a complex with no charge, a neutral complex. This is insoluble in water, and so a powdery light blue precipitate of copper hydroxide is formed. So, in our beaker, we have a mixture of all the complexes we have seen so far. These reactions are all equilibria, so everything is present. The color and proportions of the molecules in the solution is very variable and depends on the concentrations in the solution. In this case, we started with a concentrated solution of copper ions, and therefore a large proportion of hexaaqua copper ions that will be present. We then added a very concentrated solution containing hydroxide ions. According to Le Chatelier's principle, when there is a change in concentration, the equilibrium will shift to counteract this change. So in our case, when we added that large amount of concentrated hydroxide ions, the equilibrium shifts heavily to the right to use up these high concentrations of reactants, and so that makes a lot of products, that being the copper hydroxide precipitate. Since there is so much precipitate, the color intensifies, and it masks the color of the hexaaqua copper ions. So we know that addition of ammonia facilitates deprotonation. Excess ammonia, however, will undergo ligand exchange, replacing the water ligands in the hexa-aqua-copper ion with ammonia ligands. Ammonia acts as a Lewis base, and 4 of the water molecules are eventually replaced by ammonia molecules to give tetraamine diaquacopper 2+ ions. This reaction is similar to the one with the hydroxide ions, and this again is made up of a series of part reactions. This reaction eventually forms tetraamine diaquacopper 2+ ions, which is a soluble deep blue complex copper ammonia ion. The formation of this new soluble complex causes the copper hydroxide precipitate to dissolve. There are 2 equilibria involved in this. The first is the one producing the copper hydroxide precipitate. The other is the ligand exchange reaction. The hexa-aqua-copper ion appears in both of these, and so there is an interaction between the 2. The position of the new complex ion equilibrium lies to the right, using the hexa-aqua-copper ion in its formation. This means the concentration of the hexa-aqua-copper ion falls dramatically. If the concentration of this ion has fallen because of the equilibrium above, the copper hydroxide equilibrium moves to the left to replace it. Movement of this equilibrium causes the precipitate to dissolve. The neutral complex is lessened to the point where it turns back into the hexa-aqua-copper ions. This then allows for more tetraamine diaquacopper 2+ ions to be formed. To get the precipitate to dissolve, you obviously need the ligand exchange equilibrium to lie well to the right, which is caused by the excess of ammonia in the solution. We can then reverse these reactions by the addition of sulfuric acid. Sulfuric acid adds hydrogen ions into the system. Firstly, the hydrogen ions react with the ammonia molecules, forming ammonium ions, therefore removing the ammonia from the complex. This draws the equilibrium back to the left, regenerating the hexa-aqua-copper ions in the process. The restoration of these hexa-aqua-copper ions allows the copper hydroxide precipitate to form again. Further hydrogen ions join with the hydroxide ions in the ligand bonds to form the water molecules once again. We are then left with our original hexa-aqua-copper solution as shown by the clear blue solution.